An AHU retrofit does not succeed because the old fan disappears and an EC fan wall appears. It succeeds only when the same air handling duty is delivered with verified improvements. Before and after must therefore mean the same airflow boundary, the same pressure boundary, comparable air density and filter condition, a documented operating mode, and measured electrical input. Without that common boundary, two power readings tell no honest story. Begin with a baseline survey while the existing AHU is still operating. Record supply airflow, the pressure rise across the fan section, fan and motor input power, speed, damper position, filter pressure drop, coil condition, belt and sheath condition, vibration, sound, operating hours and control sequence. Capture several normal load points, not only a single full-speed snapshot. Also document faults and maintenance work, because poor belts or a blocked filter must not be credited as permanent EC savings. Map the complete AHU pressure path. Measure or estimate the losses through filters, coil, heat recovery device, dampers, attenuators, casing and duct system using the project method. Check leakage, bypass and non-uniform velocity at the coil face. The old motor nameplate and fan diameter are not a retrofit duty point. The selected array must meet the airflow and static or total pressure that the actual system requires after foreseeable filter loading and control changes. Define the after retrofit acceptance schedule before choosing hardware. Include design airflow and pressure, minimum and intermediate operating points, maximum allowed input power, sound and vibration criteria, control response, service access, and environmental limits. If redundancy is required, state the exact failure case, one module unavailable, the required remaining airflow, permitted speed increase, power limit, and whether common power or controls are inside the availability boundary. Now test the physical envelope. Measure AHU width, height, depth, axis opening, coil distance, floor or rail strength, lifting route, cable route, and service side clearance. Divide the face into modules without starving edge fans or creating a large bypass path. The frame and blanking plates must seal the fan section, while each module remains removable. A smaller footprint is useful only when inlet conditions, discharge mixing, and maintenance access remain acceptable. This Longwell hardware view shows a real 3x3 FanGrid in individual plug fan modules. It proves physical modularity, mounting faces, and service access. It does not prove a customer's energy saving or a 2024 European result. The accompanying AHU application photograph likewise shows how several plug fans can occupy one air handling section, but final quantity and performance come from the exact project curves and installation. Select the array as a system. At a common pressure, the operating fan airflows combine, but the installed result can differ from a simple catalog sum because the frame, partitions, inlet clearance and AHU resistance affect performance. Plot the array curve against the system curve for every required state. Confirm normal sharing, partial load control, the defined module out condition, per module speed and power, and any non-return or isolation strategy. Plan the conversion sequence around downtime and risk. Isolate the AHU, remove the belt drive assembly using the approved lifting and energy control procedure, inspect the casing and coil, install the engineered frame, close every bypass opening, mount the fan modules, route protected power and control wiring, restore guards and verify clearances. Temporary structural members, sharp edges, and heavy rotating equipment require a site-specific method statement and qualified personnel. Commission the controls before judging efficiency. Verify the project-specific enable, speed command, feedback, alarm, communication, and failsafe behavior. Confirm that all modules respond together when intended and that one fault does not create reverse flow or an uncontrolled pressure change. Tune the pressure or airflow loop for stable response rather than simply copying the old drive frequency. Trend commands, speed, power, and alarms through load changes. Then perform the true after test. Use the same measurement boundary and comparable operating conditions as the baseline. Match airflow and pressure first, only then compare electrical input. Recheck filter condition, damper position, air density, and instrumentation. Measure coil face uniformity, sound, vibration, current and total array power. Test the defined module out state and confirm that remaining modules stay inside their allowable speed and power envelope. Turn the measurements into an annual business case. Calculate energy for each operating mode as measured kilowatts multiplied by annual hours, then include applicable demand charges. Add documented changes in belts, bearings, filters, service labor, replacement modules, and downtime. Subtract controls, installation, commissioning, and lifecycle costs. Simple payback is installed incremental cost divided by annual net saving, but sensitivity to run hours, electricity price, and filter loading should remain visible. The final before and after package should let another engineer reproduce the decision: baseline data, required duty schedule, fan and array curves, layout, structural and electrical details, control sequence, commissioning results, module out test, measured annual model, assumptions, and acceptance signatures. For a Longwell FanGrid retrofit review, send the existing fan data, airflow, pressure, AHU dimensions, voltage, controls, load profile, and redundancy target.